Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Lesson 5, extending the domain of sine and cosine to all real numbers. Classwork opening exercise says, suppose that a group of 360 co-workers pool their money, buying a single lottery ticket every day with the understanding that if any ticket is a winning ticket, the group will split the winnings evenly and they will donate any leftover money to the local high school. Okay, so in this scenario, you could look at it two different ways. You could narrow it down to pennies or even dollars. I will do both. So using this strategy, if the group wins $1,000, how much money will be donated to the school? So the first thing I would say is, if I have $1,000 of winnings, and there are 360 people who invested money for these tickets, then 360 will only go into 1,000 twice. 3 times is too much. So 2 times 360 plus some amount. So if I go to my calculator and I say 360 times 2, well, that's 724. And if I want to know how much that is away from 1,000, then I get 276. So 276, okay? Okay, so let me just check that again. Oh, why did I put 362? Clear. 360 times 2. Why did I do 2 again? Alrighty. 360 times 2 is 720. 1,000 minus my answer is 280. Okay, so this is not 276, it's 280. So $280 will go to the school, and every participant will get $2. Okay, but if I do this a different way, and I say 1,000 divided by 360, that would be $2.77 each. So if we went down to pennies, $1,000 equals 2 times not 2, struggling here. We have 360 participants. And I divided 1,000 by 360 to get 2.77. 2.77. So if everybody took $2.77, then I would take that 2.77, because you can't go out any further than that. You can't take 7/10 of a penny. So if everybody got $2.77 times 360 people, that'd be $997.20, and that'd only leave $2.80 to the school. Okay, so there's a couple of ways of looking at it. They did not specifically say even dollar amounts. Okay, so part B says, what if the winning ticket is worth $250,000? Using the same plan as in part A, how much money will be donated to the school? All right, so 250 grand. First, let's do it by even dollars. So I'll take my calculator and take $250,000 divided by 360. And I'm only looking at the whole number, 694. So everybody will get $694 times 360 plus the remainder. So if I take 694 times 360 people, that's $249,840. That leaves $160 out of that 250. Okay. How much did I say? Yeah, $160. Okay, so $160 would be donated to the school doing this. But if we go down to pennies, $250,000 times some value times 360 plus the leftover. So look what's happening here. What are we doing? We are dividing $250,000, which I've already done, by the way. It's $694.44. It'd be $694.44 per person if we went to the whole penny. So 694.44 times 360 people totals $249,998. That only leaves $1.60. So you see what's happening here. If we go to pennies, we're just moving the decimal place over too. Okay. But we had to find this amount here. All right, so continuing this scenario, what if the winning ticket is worth $540,000? Well, $540,000 equals some amount divided by evenly to 360 people would be 540 divided by 360, and that will give me $1,500. $1,500. And as you can see, there was no remainder, so the school gets nothing. Every participant got $1,500, and there was no money left over to donate to the school. Okay, so on the previous page, let's just focus on what we did, not counting the pennies, okay? And let me explain what we were leading up to. Notice the 360 people. They made that equivalent to the number of people as equal, or the number of people, coworkers, equivalent to the number of degrees in a circle. So if I wanted to go around a circle 1,000 degrees, I would rotate 2 full rotations, and then there'd be a leftover of 280 degrees. And that's what we're leading up to. We can get on a Ferris wheel, and we're going to rotate. We're not just going to get on the Ferris wheel and rotate once and get off. We could rotate twice. We could do 2 full rotations, 3 full rotations, 4, 5. We could be on there for a half an hour and do 15 rotations. Doesn't, the possibilities are endless. So what that was trying to lead us to is to understand that if we're given a value of more than 360 degrees, then what that means is if I take my, what's going on here? All right, let me just draw a new line because it's exploded. There we go. So if I take this line and rotate it around, if I go around, there's 90 degrees. Here's 270 degrees. I'm sorry, 180. Here's 270. And all the way back around to 360 degrees. But we're going to continue because this first problem says 405 degrees. So what we're going to do is say, well, in order to answer this question, 405 degrees equals 360 degrees plus another 40 to get us to 400 and another 5. So that would be 45 degrees. So we're going to do one full rotation. So let me do that again. We're going to start here, 90, 180, 270, 360, and then another 45 degrees will get us to 405 degrees. Okay. So a 45-degree rotation would place us at the same location as 405 degrees. So therefore, the measure of the angle, it says here, find the cosine of 405, the sine of 405, identify the measure of reference angle. So the reference angle is just simply the number of 360s, the number of times we can multiply by 360 to get a number, and then the remainder is our reference angle. Hopefully that makes sense to you now. So what we're going to do is we're going to mark this as our reference angle right here of 45 degrees. Okay, So since our reference angle is 45 degrees, then we are going to draw a straight line down like this, and that makes a right angle. And it's a 45, 45, 90 triangle. So if this is 1, if x equals, this is x root 2. If x square root 2 equals 1, then we divide by the square root of 2 on both sides. And we get x equals, because these cancel, and we get square root of 2 over 2 when we rationalize the denominator. So this point right here is the square root of 2 over 2, comma, the square root of 2 over 2. And now hopefully you remember that from the diagram in lesson 4, the last page, and you really should learn all the reference angles around in 30 and 45 degree increments. Okay, so now we can simply answer this answer these questions. So now the cosine of 405 degrees equals the cosine of 45 degrees, which equals the square root of 2 over 2. That is our x value. Cosine is here and sine is here. So then I'd say the sine of 405 degrees equals the sine of 45 degrees, and that is also the square root of 2 over 2. Alrighty? Okay, so now let me erase all this. And we will bring our reference angle back down to 0, like so. Okay? Now it says find the cosine of 840. So I would say the cosine of, actually before I even do that, let's just say what 800, find the reference angle. So you say 840 degrees equals 2 times 360 degrees. So that's going to be 2 full rotations, bringing us to 720, and 840 minus 720, 772. Sometimes I wonder. 720 would be 120 degrees. Okay? So 840 is 2 times 360 plus 120 degrees. And this is our reference angle, because this 2 times 360 or 720 is simply taking our initial ray, going around 1 rotation is 360, going around 2 rotations is 720, and then another 90 and 120 degrees. Okay, 90 and 30, so it'd be about right here. Okay, so then I would draw a straight line down like so, and this is a 90-degree angle. So if this is 90 degrees and this is 120, 120 minus 90 equals 30. So if this is 30 degrees, then this has to be 60 degrees because this is 90. So this is a 30, 60, 90 right triangle. Okay, so this distance is x. This distance is 2x, and this is x root 3. So since my 2x equals 1, we're doing a unit circle. If 2x equals 1, then we divide both sides by 2 to get our x. So x is a half. So now I'm going to replace these two values. This is 1/2, and this is root 3 over 2. So this is the point, negative 1/2. We went left a half, and then up square root 3 over 2. And there's our cosine, and there's our sine. So now I'm going to answer the question. So then I say the cosine of 840 degrees equals the cosine of my reference angle, 120 degrees, and the cosine was negative 1/2. The sine of 840 degrees equals the sine of our reference angle, 120 degrees, and that is the square root of 3 divided by 2. Okay? Okay, so what I'm going to do now is over here, I'm going to make a little table. So 1 times 360 equals 360. In other words, that's 1 full rotation. 2 full rotations, 2 times 360 is 720. 3 times 360 is 3 times 0 is 0. 6 times 3 is 18. Carry the 1. 3 times 3 is 9. Plus that 1 is 1080. So I'm looking over here at these larger numbers. We want to go all the way up to over 2000. So 4 times 360 equals 4 times 0. 6 times 4 is 24. 4 times 3 is 12. Plus those 2 is 1240. 5 times 360, or 5 rotations, is 0. 6 times 5 is 30. Carry the 3. 15 plus 3 is 18. Okay, 1800. 6 times 360 would be 1800 plus 360, which would be 2160. And we're far enough. So we're going up to, on this page, only 6 full rotations. Okay, so now I want to find the cosine of 1680. So the first thing I'm going to do is say 1680. Hang on, let me change colors. Let me go green. 1680 degrees equals, I come over here, and it's more than 4 but less than 5 full rotations, so it's 1240. So 1680 is 1240 degrees plus, I need 40 to get to the 80. Actually, did I miss one? This isn't 1800. All right, so let me just fix this. 360 times 4 is 1440, not 1240. Okay, so this is 1440. This is 1440. Oh my. Uh, 360 times 3 is 1080, that's right. And 360 times 5 should be 1800. Okay, there we go. That's better. So 360 times 4 full rotations is 1440. And I need 1680. So the 40 plus 40 will give me the 80, and I need 200 to get to 600. 4 to 2 is plus 2 is 6. So 1440 plus 240 equals 1680. So this is my reference angle of 240 degrees. So now I would say the cosine of 1680 degrees equals the cosine of 240 degrees, which equals, and now I take my reference angle here. Let me erase everything in the circle. Okay, and I'm going to now bring this back here. And again, I need to make you understand that, help you understand that 1440 degrees is 4 full rotations. So 1, 2, 3, 4, and then we want to go another 240. Well, 270 is right here. So I need to go back 30 degrees. Okay, so now if I draw a straight line, why is my pen not working? Here's my right angle. This is 30 degrees here, so this has to be 60 degrees. So the cosine of 240 degrees is equal to the cosine of 60 degrees. But remember that cosine is negative in third quadrant. So it'd be equal to negative 60 degrees. So the cosine of 240 equals the negative cosine 60 degrees, which equals, so remember that this is 2x, so x is a half, and this is root 3 over 2. And it's negative. Actually, that is a half. Let me just do the table here. This is a distance of square root of 3 over 2. It's negative. And this is a distance of 1/2, and it's negative. So my cosine is my x. So this is negative 1/2. The sine of 1,680 degrees equals the sine of 240 degrees. And I'm putting parentheses around these for a reason. And the sine in the third quadrant is also negative. So I'll say the negative sine of 60 degrees, which equals a negative, and the sine of 60 is opposite, negative root 3 over 2. Okay, just need to be careful with these values. I need to be more careful. So here we go, next one. So let me bring my reference, that is my initial ray, and where does it terminate? 2,115 degrees. It's more than 5 full rotations, but less than 6. So the first thing I would say is not the cosine, just the value itself first. 2,115 degrees equals 1,800 degrees plus 315 degrees. And there is my reference angle. Sort of. Remember, reference angles are the angle between the terminal ray and the x-axis. So then what this means is I'm going to do 5 full rotations, which would get me back to here, and then go another 315 degrees. So here's 270, and then I'm going to go another 45 degrees. So 315 is right there. So then I ask myself, what is the reference angle? And this is 45 degrees. So since that's 45 degrees, this is a distance down of square root 2 over 2. And this is a distance over square root 2 over 2. So my cosine is root 2 over 2. My sine is negative root 2 over 2. And that's what I state. So I say the cosine of 2,115 degrees equals the cosine of 45 degrees, which equals square root of 2 over 2. The sine of 2,115 degrees equals the negative sine of 45 degrees, which equals the negative square root 2 over 2. Okay, this question had me puzzled for a moment. Whenever you have degrees and there's a separation, I'm thinking 720 degrees and 30 minutes, because less than a degree is minutes, and then you can take even less than that and go down to seconds, and it kind of comes from the clock. So a less than a degree would be a minute or second, but in this case, all they meant was this is 720,030 degrees. Okay, so I'm going to use my calculator for this. I'm not going to make a table that goes out that far. So I'm going to take 720,030 degrees and divide it by 360. And that is going to give me 2,000 rotations with a remainder. So the first thing I'm going to do is say 720,030 equals 2,000. So let me think about this a second. It'd be 2,000 times 360 degrees. And now if I do that, I'll find my remainder. 2,000 times 360 is that 720,000. And I have a remainder of 30 degrees. So that'd be plus 30 degrees. So this is a 2,000 rotations around the circle, getting back to the beginning, 2,000 times around, ending up here, and then going another 30 degrees, which is about here. Okay, so then I draw this down. There's my right angle. This is 30-degree reference angle. And I had to go over square root 3 over 2 and up a half. Okay, you start to get familiar with these values. So then I will answer the question and say the cosine of 720,030 degrees equals the cosine of 30 degrees, which equals cosines the x square root of 3 over 2. And the sine of 720,030 degrees equals the sine of 30 degrees, which equals 1/2. Okay, so there's exercises 1 through 5. Okay, exercise 6 through 10. Now we're going to do negative degree measures. All that is, don't panic, it's just rotating clockwise. So if I take my reference angle here, or my terminal, not my reference angle, but my initial ray, and rotate in the clockwise direction, that's negative degrees. So if I go down here a negative 30 degrees, this would be negative 30 degrees right here. It's 30 degrees going this direction. Okay, so now I would have my triangle here, and opposite 30 is a half, and opposite adjacent to 30 is root 3 over 2. Okay, so it says find the cosine of negative 30 degrees. So the cosine of negative 30 degrees, since we're in the fourth quadrant, cosine's positive, that's going to equal the cosine of 30 degrees, which equals the square root of 3 over 2. Okay, but the sine of negative 30 degrees equals, since we're in the fourth quadrant, sine's negative, it's equal to the negative sine of 30 degrees, which equals negative 1/2. Okay, and that's all you really need to do with the direction change. Just be careful of your quadrants and what's positive and negative. Okay, page 3 brings us to more negative degrees. So we're going to be working clockwise on this page. Okay, so it's really not anything different. So I'll go a little quicker. Find the cosine of negative 135 degrees. So we start at our terminal, or our initial location of 0 degrees, but we're going to go counterclockwise or clockwise for negative. So clockwise rotation, 90 degrees is here. There's negative 90 degrees. I need to go another 45 degrees to get to negative 135. And then I just draw my quick little perpendicular to the x-axis, like so. There's my right triangle. And since this is 45, you just start to remember that the values are square root of 2 over 2. And I'm going to the left, so that's negative. And we're going down, so that's also square root 2 over 2 negative. So there's my cosine, here's my sine. So in answering this question now, we would say, first of all, let's say negative 135 degrees is equal to 45 degrees. Okay. So if you think of it this way, if this is negative 135, you can also go the other way so you're not confused. If you know rotation is 360 degrees and I subtract 135 from it, then I get 5, 2, 2. So if I go this distance, rotate this number of degrees, which is 135 degrees, full rotation is 360, so this side would be 225. So I could also think of this as being a rotation counterclockwise 225 degrees, which is positive to get us here. And I would say the cosine of negative 135 degrees is equal to the cosine of 225 degrees, but we still want the reference angle, and 225 is 180 degrees plus 45 degrees. So that would equal the cosine of 45 degrees. Okay? Okay. But cosine in the third quadrant is negative. So cosine 225 is equal to the negative cosine of 45 degrees, which equals a negative square root 2 over 2. Sine of negative 135 degrees equals cosine, or sorry, sine, not cosine, equals the sine of 225 degrees if I want to switch it to positive. And that's equal to, and sine is negative in the third quadrant, and my reference angle is 45 degrees. So it's the negative sine of 45 degrees, which equals a negative square root 2 over 2. Okay, number 8. So I'm going to leave this back to 0, starting a new problem. Find the cosine of 1,320, negative. So go to the calculator the easiest way and say 1,320 divided by 360 is 3 and a remainder. So then I say, well, 360 times 3 is 1,080. And then my remainder is the difference between the two. So then I'd say, well, 1,320 minus 1080 is 240 degrees. Okay? So what I'm trying to point out here is sometimes the calculator makes it easier. A negative 1,320 degrees is 3 full rotations in the clockwise direction and then another 240. So we would 1, 2, 3, and then another 240, which is 180. Okay, and then 180. And how many more degrees do I need to get to 240? Well, it's 60. So that'd be up here. And then I draw my arc down here, or my side of my triangle, my vertical distance. This is 60 degrees because we had to go 60 more than that 180 to get to 240. So since this is 60, this is 1, this is 1/2, and this is the square root of 3 over 2. My half is negative. I went left. So there are my values I'm going to use. So I would say the cosine of negative 1,320 degrees equals the cosine, just kidding, second quadrant, the negative cosine of 60 degrees, which equals negative 1/2. The sine of negative 1,320 degrees equals the sine of 60 degrees, which equals the square root of 3 over 2. Okay, number 9. It says to find the cosine of negative 2,205 degrees. So get my calculator. And I'm not going to worry about the negative right now. 2205 divided by 360. That will give me the full rotations of 6. Okay? Well, 0.125 is an eighth. So what's an eighth of 360? We can do it that way. But I'm going to do it this way. I know 6 full rotations. So 360 times 6 will give me 6 full rotations of 2,160. And the difference between the 2205 and the 2160 is my angle. So 2205 minus 2,160 equals 45 degrees. Okay? So what that means is, how many full rotations was that? 6. So coming back here, take your initial ray, rotate it around clockwise 6 times. So you go around 6 times, okay? And then an additional 45 degrees. Okay, 45 degrees was our remainder. Then draw your perpendicular to your x-axis, and you have a right triangle, which is a 45 degree triangle. So this is down, so it's a negative square root 2 over 2, and this is positive square root 2 over 2. So then I would say the cosine of negative 2,205 degrees equals, cosine's positive in the fourth quadrant, so it's equal to the cosine of my reference angle of 45 degrees, which equals root 2 over 2. The sine of negative 2,205 degrees equals the negative of the sine of 45 degrees, because sine is negative in the fourth quadrant, and that's going to give me a negative square root 2 over 2. All right, number 10. Okay, so now I want to find negative 2,835 degrees. So we do 2,835 divided by 360, and we get 7 full rotations. So I take 360 times 7, and the difference between 2835 and 2520 is my angle. So 2,835 minus 2,520 equals 315 degrees. Okay, and so I want my reference angle, a full rotation. So 315 degrees would be all those rotations. How many was it? 7. So we rotate around 7 times, and we go to 315 degrees, which is, here's 270, and it's over here somewhere. And to find my reference angle, it's 360, the full rotation to get back to my x-axis, minus that 315 will give me 45 degrees. So now I am right here at 45 degrees. I then draw a vertical to the x-axis, and this is a right angle. This is 45 degrees. They're both positive. This is the square root of 2 over 2. This is the square root of 2 over 2. So then I'd say the cosine of negative 2,835 degrees equals the cosine of 45 degrees, which equals the square root of 2 over 2. The sine of negative 2,835 degrees equals the sine of 45 degrees, which is also the square root 2 over 2. Now let me point something out to you. I could have simply just gone in my calculator and see what happens. So if I go to mode, make sure I'm in degree measure, go back to the home screen, and if I say cosine negative 2,835 and hit enter, I got 0.7071. And if I take the square root of 2, the square root of 2, divide it by 2, I should get 0.70716. All right. So if you have a calculator, you can just put this in your calculator, but what you're not doing is understanding where these come from. If you just punch numbers in a calculator, you are not learning anything. You're just getting the answer. We're not here to just get answers. We're here to understand a concept. All right, discussion, case one. What about the values of the sine and cosine function of other amounts of rotation that produce a terminal ray along the positive x-axis, such as 1080 degrees? Our definition of a reference angle is the angle formed by the terminal ray and the x-axis, but our terminal ray lies along the x-axis, so the terminal ray and the x-axis form a zero angle. How would we assign values of cosine of 1080 and sine of 1080? Okay, so, well, here's what I would do. So first thing I would do is check that. So 1080 divided by 360, and I remember that on the last page, it's a 3 full rotation. So here's how they're showing this. 1, 2, 3. It's like a coil spring. 1, 2, 3. So you start at your beginning, and how many times did you go till you got to the end? 1, 2, 3. We are at here at 0. We're on the x-axis. This is a unit circle. Here's the key. The radius is 1 squared, right? X squared plus y squared equals r squared. My radius is 1. So this is a distance of 1. So my x is 1. And how much did I move up off of the x-axis? I didn't. So this is the point 1, 0. All right, so we're going to use that coordinate P as 1, 0. So the cosine of 1080 degrees equals the cosine of 0 degrees. Okay, that's how many degrees it is if we're right on the x-axis. If it was over here, that'd be 180 degrees. Okay. So, and then the cosine of 0 degrees, this is cosine and this is sine. So the cosine of 0 degrees is 0. And then I'd say the sine of 1080 degrees equals the sine of my reference angle, 0 degrees. And the sine of 0 is 0. Okay, page 4 brings us to a misprint. All right, so let's fix this. We're trying to solidify a concept here, and there is an error in the book, and that really drives me nuts. So there's an error here. It says, what if we rotated around 24,000 degrees, which is 400 turns? Well, no, it's not. 400 turns when there's 360 degrees in a circle, whoops, is 144,000, not 24,000. So this should say, so fix your book, cross this out and write 144,000. Whoops, dollars. Yeah, I should get paid that for finding the error. 144,000 degrees. So what is the cosine of 144,000? And what is the sine of 144,000? All right, so if we do this, now if I check my calculator, 144,000 divided by 360 degrees should give me 400. There it is. So it's 400 full rotations. It would have us starting at this initial ray right here, going around 144,000 times, actually, yes, that way, counterclockwise, landing right there at the beginning. Again, that is going to be the point 1, 0, where this is cosine and this is sine. So the cosine of 144,000 degrees equals the cosine of 0 degrees, which equals 1. The sine of 144,000 degrees equals the sine of 0 degrees, which equals 0. So if theta equals n being the number of rotations times 360 for some integer n, no decimals, fractions, then the cosine of theta is always going to be 1 and the sine of theta is always going to be 0. Because if I go back to the last problem on the previous page, we had 1080 degrees with 3 rotations, and that's put us at the terminal ray being at the initial ray, and therefore at the point 1, 0 on the unit circle. And I have an error here. The cosine of 0 is 1. I think I said 1 and wrote 0, maybe not. But the cosine of 0 degrees is 1, and the sine of 0 is 0. So no matter how many rotations, we get cosine of 1, sine of 0, 0. And so no matter what n is, cosine of theta is always going to be 1, and the sine of theta will always be 0, so long as we have multiples of 360. Okay, move on to case 2. What about the value of the sine and cosine function of other amounts of rotation that produce terminal ray along the negative x-axis, such as 540 degrees? So if I take my calculator and say 540 divided by 360, that is going to give me 1.5 rotations. So I'm going to start here, rotate 1.5 times from here. So it's going to go around once and then another half. We will end up with our P point being right there at 180 degrees. So I'd say the cosine of 540 degrees equals the cosine of 180 degrees, which equals, and what is this value here? Remember, radius 1, this is a distance of -1. So I went left 1, up 0, and this is my cosine, and this is my sine. So the cosine of 180 degrees equals -1, and the sine of 540 degrees equals the sine of 180 degrees, which equals 0. Okay, so now let's try 900 degrees. So I take 900, divide it by 360 to find my n, and that's 2.5 rotations. Again, 1, 2.5 puts me right there again. I didn't realize I had my eraser on. So there's P again at the same location, -1, 0. So the cosine of 900 degrees equals the cosine of 180 degrees, because it's 2.5 rotations, and the cosine of 180 degrees is -1. The sine of 900 degrees equals the sine of 180 degrees, which equals 0. So state the generalization of this result. If theta equals n times 360 plus another 180, which is our half rotation, so that's our 1.5, 360 plus 180, 720 plus 180, then the cosine of theta will always be -1, and the sine of theta will always be 0. Okay, page 5, case 3. What about the values of the sine and cosine function for rotations that are 90 degrees more than the number of full turns, such as 630? So if I go into the calculator here, remember, -630 is a clockwise rotation, but if I take 630 degrees divided by 360, I get 1 3/4 turns. So that means, okay, so what does that mean? -630 degrees is, what did we say? 1 3/4 rotations. So that means this is going to rotate clockwise because it's negative. So rotate this around, there's 360. And then 3/4 of the way around would get us 1/4, 2/4, 3/4 right here. Okay. So if I were to show this as a rotation, let me do that. We started here. We went around one full rotation and then around 3/4 more. So that was 1 3/4 rotations. And we are now at 90 degrees. So we would say, well, what is this? We went over 0 and up 1, which is my radius. So it's the 0.01 is my P. So what we would say is cosine of negative 630 degrees equals the cosine of 90 degrees, which equals 0. Remember, cosine comma sine. The sine of negative 630 degrees equals the sine of 90 degrees, which equals 1. Can we generalize to any rotation that produces a terminal ray along the positive y-axis? Well, yes, of course. Yes, we can. State the generalization of these results. Well, if theta equals n times 360 plus another 90 degrees, or if we went clockwise, like we did here, it'd be n times 360 plus 270 degrees, or minus 270 degrees, I should say. Okay, so here they're giving a generalization of a counterclockwise rotation. If theta equals n times 360 plus 90 for some integer n, then the cosine of theta will equal 0, and the sine of theta will equal 1. So you really need to be careful about what they're saying here. What they mean and what they say are two different things. Because if I rotated 1.75 times like I did here, and n is 1.75, okay, like that, 1.75, 1.75 times 360 would be 1 times 360 times 3/4 of a rotation is not 90 degrees. It is 270 degrees. Okay, so just be careful with how they're saying this, but what they mean is when we're doing a clockwise rotation, they should have used a positive degree here to explain this. All right, case 4. What about the value of the sine and cosine functions for rotations whose terminal ray lies along the negative y-axis, such as negative 810 degrees? So if I take my calculator and say 810, it's off, hang on, hello. 810 divided by 360 equals 2 1/4 rotations. Okay. So 2.25 rotations is 1, 2 1/4. That would be 360 degrees plus 270. So let me think about, I'm down here too far first. So first it says, what about 810 degrees? And that's what I did. That's 2 1/4 rotations. So starting here, going negative is clockwise. So 1, 2 1/4 would put me right here at the point 0, comma, -1. Remember, this is cosine and this is sine. How would we assign the values of cosine negative 810? We would say, well, we'd say the cosine of negative 810 degrees equals, and that would equal the cosine of, and here we could either say 270 degrees, or we could say negative 90 degrees, but I'll say the positive 270 degrees, and that is going to equal 0. Okay, and now doing sine, we would say, well, the sine of negative 810 degrees equals the negative sine, because sine is negative in quadrants 3 and 4, and we're on the y-axis, which is between 3 and 4, so everything in between is also going to be negative. And so negative sine of 270 degrees is going to give us negative 1. Can we generalize? Yes. And the generalization is if theta equals n times 360 plus another 270 degrees, or 3/4 of a rotation for some integer n, then the cosine of theta is 0 and the sine is negative 1. All right, page 6 brings us to a discussion. It says, let theta be any real number. In the Cartesian plane, rotate the initial ray by theta degrees about the origin. Intersect the resulting terminal ray with the unit circle to get a point x sub theta, comma, y sub theta in the coordinate plane. The value of sine theta degrees is y sub theta, and the value of cosine theta degrees is x sub theta. So I've already explained that to you. It's x comma y cosine comma sine. So what is the domain of the sine function? The domain of the sine function is all real numbers. Okay? What is the range of the sine function? Okay, the range of the sine function. So the domain of the sine function, we could go around over and over and over and over, multiple rotations, infinitely many rotations, and that's why it's all real numbers. The range of the sine function is going to be limited to negative 1 and 1. Okay, with the unit circle, we don't go greater than 1, we don't go less than 1. That is our radius of our circle. Okay, carrying on with this, what is the domain of the cosine function? Again, that is going to be all real numbers because we can rotate infinite number of times. And then what is the range of the cosine function? Well, the cosine function is your x-axis, and using a unit circle, the radius is 1, and therefore 1 and negative 1 are our extremes, and therefore the range of the cosine function is negative 1 to 1. Okay? Okay, page 7 brings us to the end of lesson 5. Review the lesson summary and go to your problem set.